So, if you recall, in our last lecture we talked about how we can select the I/O device interfaces in the form of the I/O ports for carrying out input and output, for selecting the devices. Now, in this lecture and the next few lectures we shall be talking about in some detail how the actual data transfer takes place between the I/O devices and the processor, and what are the different variations that are possible there. Okay. So, the topic of today's lecture is data transfer techniques. So, broadly speaking, when we talk about data transfer techniques, we basically talk about a scenario like this. We have the CPU, we have the memory, and we have the I/O devices. Now, when you talk about data transfer, you may be tempted to think that we are actually thinking about data transfer between CPU and I/O, but it is not exactly that. So, data transfer or input output transfer actually takes place between I/O and memory devices, because suppose it is an input device, the CPU after reading it will write into memory, and if it is an output device, CPU will be reading some data from the memory and write it into that, because CPU is just a mediator. Whatever data it is transferring, that will be there in memory. So, although this line is like this, it is actually via CPU, something like this. Okay. So, there are several alternatives available here. That is what is mentioned or explained in this slide. So, under the data transfer technique, the first broad approach can be called as programmed data transfer. Programmed means, as the name implies, CPU will be executing a program that transfers data between I/O device and memory. Meaning, suppose it is an input device, let us say we are using memory mapped kind of device interfacing, then CPU will have to execute a program that will be loading some data from the memory from that device, and it will be storing it into some memory location. Suppose there are 100 data, this has to be done in a loop, 100 times it will repeat it. So, there will be a program which will be running, which will be actually reading the data from the input device and which will be writing the data into the memory. Okay. Now, this is true for programmed I/O techniques in general, but under programmed again there can be three variations: synchronous, asynchronous, or interrupt driven. We shall be looking into the detail of this later. The other alternative is direct memory access or DMA. Well, here the CPU has very minimal intervention. CPU does not execute any program. Rather, there is a separate external controller that will directly transfer data between I/O device and memory without disturbing the CPU. CPU may be continuing with whatever it was doing. Okay. So, it will be directly transferring the data between the I/O device and the memory. So, this is what DMA is: external controller directly transfers data between I/O device and memory without CPU intervention. Now, let us look into these methods one by one. Synchronous data transfer. Well, synchronous, this name implies that there is some kind of a transfer going on, there is a sender, there is a receiver, and both of them are synchronized. Synchronized roughly means that both of them knows what is the speed of data transfer. Suppose I know some data is coming to me, I know what is the speed with which it is coming to me. So, So, I can pick up the data one by one with that speed, well if the speed is known to me. Okay. If I know that data will be coming to me one every second, so in every second I will pick up one new data. This is synchronous. Okay. So, this is what is mentioned here. The I/O device transfers data at a fixed rate that is also known to the CPU. So, here the CPU will be initiating the I/O operation whenever it wants to, and after it does so, the CPU will know that the data will get transferred in fixed rate. So, giving some fixed time delay, the CPU can read or write the bytes or words one by one. Now, there are some characteristics in this method, that while the CPU is waiting with the time delay, CPU does not have anything else to do, CPU will lie idle. This is one major problem, that you are having very poor CPU utilization. Second thing is that you will find very few I/O devices which have this kind of synchronous behavior, that data will always be coming at fixed data rate, fixed speed, fixed rates. It is very rare, you know. So, you will not find many devices like this. So, how this works, I am just showing it in a flowchart form here. So, the steps are roughly like this. So, you initiate, CPU initiates the data transfer. After initiating, CPU will know that now the data will be coming, suppose it is an input device, data will be coming at a fixed rate. So, CPU will give that amount of time delay, it will read the next word from the I/O device, it will write that word into memory, then it will check whether all the words have been transferred or not. If it is no, it will again go back, again wait for a time delay and read the next word. So, this will repeat, and if it is done, so the CPU will know that data transfer is complete, it will continue with the next step. Now, you see here the CPU is reading the data after giving fixed time delays, because it knows the date. So, if there is a mismatch in the speed due to some problem, the I/O device is not able to send the data at that fixed rate, then obviously CPU will be starting to read the wrong data, because CPU is expecting the data to come every time t, but if the device is a little late, so it may be reading the old data. Okay. So, some error may occur if the input device and the processor gets out of sync. This is one problem. Because of the same reason, large number of words cannot be transferred in one go, because chance of the two devices getting out of synchronization will be high. And third thing is that you see there is a program which is executing. So, you are reading from I/O module, writing into memory. So, if we think of the speed of data transfer, what is the maximum speed we can achieve? So, the maximum speed of data transfer does not depend only on the speed of I/O device and memory, but also on the execution time of this code. This is true for all programmed I/O techniques. The basic code where you are reading a word from module and writing into memory, this will take some time and this will limit the maximum data transfer rate, right. Okay. Now, let us move on to the next method, asynchronous data transfer, well, which is more practical, because you will not find many devices in real life which are strictly synchronous in nature. So, in asynchronous, what are the characteristics? Here it is assumed that the CPU does not know or need not know when the I/O module will be sending the next data. So, CPU does not know beforehand, the next data may be coming next millisecond or maybe after 1 hour. So, the CPU has to continuously check the status of the IO device whether it is ready. So, it is continuously asking the device, are you ready, are you ready, are you ready. As soon as the IO device says yes, I am ready, then the data transfer takes place. So, you can see the CPU is wasting its time just asking the status of the device, are you ready, are you ready. During this process, the CPU is doing nothing useful, it is simply checking the status, right. So, here as I said, the CPU has to check the status of the IO module to know when the device is ready to transfer the next word. So, CPU has to check the status of the IO module, because CPU does not know when the next data is coming. It will continuously have to check the status of the IO module, and this process is called handshaking. So, CPU and the IO module are doing some kind of handshaking, by virtue of which it comes to know when it is ready, the device is ready to transfer. So, some of the characteristics as I said, that while the CPU is checking the status of the IO module, it cannot do anything else, it is just waiting. So, this is obviously wasteful of CPU time, particularly for slow devices like keyboard or mouse, because for the entire period the CPU is waiting to check the status, right. This is very wasteful. So, in terms of a flow chart, the asynchronous data transfer works as follows. CPU will initiate data transfer, then CPU will read the status of the IO module to check whether it is ready or not. If it is not ready, it will go on repeating this. It will continually check the status until or unless it is ready. Now, as soon as it is ready, it can read the word from the IO module and write the word in memory. The data transfer can be done, and then it checks whether all the data have been transferred. So, if not, it again goes back and starts this process, and if it is yes, the transfer is complete and it proceeds with the next step. Now, as I said, in this loop lot of CPU time is wasted, because during this time the CPU is not doing anything useful, just checking the status of the IO module whether it is ready. So, clearly this method cannot be used for high speed devices, and just like the previous method, the speed of transfer depends also on the execution time of the code and not only on the speed of IO device and memory, right. So, synchronous and asynchronous data transfer method, these two methods we have seen, they are quite similar. In one case, the CPU does not wait for the IO device, because CPU knows when the next will be available. Suppose if you take an analogy, so I have asked you to do some work, I know that you will take 10 minutes. So, I just come after 10 minutes and take it from you, I do not ask you anything. And in asynchronous means, I give you a task, I continuously come every 10 seconds and ask you that you have done, you are done, you are done. So, means I am continually engaged here. Okay. This is the main difference between these two. So, now let us move to something which is more practical. The next step we will be doing that, but before that let us see some examples of this asynchronous method. This asynchronous method or handshaking that we have talked about, this can be used not only for data transfer between CPU and some IO device, but also for data communication purposes. One example we shall be giving. So, this example that you are showing here, this is an example of asynchronous data transfer. So, let me explain what is this meaning. There is a sender there is a receiver. Sender will be sending a sequence of bytes to the receiver sequentially. Okay. What we are saying, assuming is that the devices are asynchronous at the level of bytes, means the receiver does not know when the next byte will come. It can come immediately, it can come after 5 minutes, it can come after 10 minutes. So, it is asynchronous at the level of the bytes, but once a byte is coming, the bits within the bytes are synchronous, because once a byte have started to come, so within that byte the bits are coming with fixed delays, that is synchronous. This is a very realistic assumption in communication systems. Now, let us see how this data transfer is taking place. Let me explain. Suppose I have to transmit a byte. There are 8 bits, let us call them B7, B6, B5, B4, B3, B2, B1, B0. Now, we define something called a frame format. What is a frame format? What we are saying is that this signal that we are transmitting, this will go 0 at the beginning, and this 0 is called the start bit. So, whenever this signal goes 0, the receiver will know that a new byte is coming. So, once it has done this, the 8 bits can be transmitted one after the other. So, here the 8 bits are transmitted, let us say B7 first, then B6 dot 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 up to B0. And at the end I am leaving the line high for 1 or 2 cycles. I am calling this as stop bit. Stop bit or stop bits. So, when I am transmitting a number of such bytes, there will be a start bit, there will be a stop bit. So, how will it look like? It will begin with a start bit, then the bytes will come, bits of the byte, then the stop bit, then again a start bit will come, then again the byte, then again the stop bit, and so on. So, the receiver will always be looking for the start bits. Again a start bit can come here. So, once a start bit is found, it will know that immediately the next 8 bits are the data bits, that is coming in fixed intervals of time. So, after some fixed delays, it can read them out, right. So, exactly this thing is shown in this slide. If you just look at, the sender is transmitting 2 bytes, one is 1101 0010 and 0010 1110. So, you see at the beginning we have a start bit, it is going to 0, then 1 1 for 2 time units it is high, 0 1 0 0 1 and 0. At the end it remains high again, this is your stop bit, and when the next byte is transmitted again it is going 0. So, first bit is start bit. After that there are 2 more zeros, it remains 0 0 0 1 0 1 1 1 remains for 3 time units, then 0, then again stop bit. So, you see this is also an example of an asynchronous data transfer, where somehow the receiver is checking ready ready ready. How it is checking? It is checking whether stop bit has come, whether stop bit has come, it is checking for the stop bit, not stop bit, start bit, sorry, it is checking for the start bit. So, that start bit is a way of indicating that a new byte is coming. So, the receiver continuously check whether the start bit is coming or has appeared, the line has gone to 0 or not. Once it has found that, it will simply read the next 8 bits of the byte. This is a very classical example where asynchronous I/O is used. This is what I have just said. So, the receiver will wait for the next start bit, that will indicate the beginning of the next byte transfer, and once the start bit is received, the receiver knows the data rate, it will give appropriate bit delays and read the 8 bits, and the stop bits between the 2 bytes serve the purpose of synchronization, because if you do not give the stop bits, then one byte and the next byte might be joined together and the receiver might get confused. So, it is always good to give some gap in between and again resynchronize at the next start. So, sender and receiver will get resynchronized, right. Okay. So, the third and most important kind of data transfer technique that we start discussing on is called interrupt driven data transfer. Well, let me first tell you the analogy what it is. Say I come and I give you a task, I ask you do this, but I am not asking you continuously that whether you have finished, whether you have finished. I give you a task, I go back and I start doing my own work, something else I am doing. So, you finish your task and as soon as you are done, you come to me and tell me that well I have done, I have finished. So, whatever I was doing, I will keep it. I say okay, you have done, let me see, I will see what you have done, is fine, it is done, then I will again come and resume whatever I was doing. This is the basic idea behind interrupt driven data transfer or interrupts in general. Okay. Let us see. So, whatever I have said in the terminology of computers, it is like this: the CPU initiates the data transfer and proceeds to perform some other task. So, it is not sitting idle, it is doing some other task. So, when the I/O module is ready for data transfer, it informs the CPU by activating a signal called interrupt request. Like someone is coming to the CPU and telling that well I am ready. So, when the interrupt request comes, the CPU which was doing some other task will suspend that task temporarily, service the request whatever interrupt request is coming. So, in this case it is for a data transfer. So, it will do the data transfer and it will return back to that some other task it was doing, right. So, it is something similar to a subroutine or a function call or return. Whenever an interrupt comes, I go somewhere, I finish it and then again I come back. So, some of the characteristics here are that the CPU time is not wasted while checking the status of the I/O module, because we need not check the status. The device itself will come and tell me that I am done, I have finished. CPU time is required only to carry out the data transfer, plus of course, some overhead for transferring and returning of the controls. So, stopping the process, going there and again coming back, this extra overhead is there, but in addition to that the CPU time can be utilized in a much better way. CPU can do something more fruitful, some other task, right. So, pictorially let us see how it looks like. CPU initiates the data transfer, and after initiating the data transfer, CPU is performing some other task, and the device, when it is ready, the I/O interface, it will send an interrupt request to the CPU. Interrupt request will tell the CPU that well I am done, I am finished. So, when it is coming interrupt request, then the then what will happen? CPU will temporarily suspend this work, whatever it was doing. It will read word from IO module, write word, do the data transfer, check whether all the words have been transferred. If it is yes, done. If no, it will resume this other task, whatever it was doing, and it will be waiting for the next interrupt request to come. Okay? So, next interrupt request means another data transfer. Fine. Okay. Now, this part of the code which gets activated whenever interrupt request comes, in this case a simple data transfer, is called interrupt handler or interrupt service routine ISR. Now, here since we are more concerned about IO transfer, we are talking about interrupts for IO, but interrupt is a general concept. Interrupts can come from or for other reasons also, like interrupt may be coming from a timer in a time sharing operating system, interrupt may be coming from internal to the processor, like there is a division by 0, or there is a power failure, the power is falling, there is a sensor. There are so many sources of interrupts. Okay? So, depending on that, exactly what you do inside your interrupt handler or ISR may be different, but here because we are concerned only for IO transfers, so the ISR's sole task will be to transfer the data. Okay? Fine. So, some features of interrupt driven data transfer are as follows. You see, as I said, there is some similarity with a function or a subroutine call, that when an interrupt request comes, you stop what you are doing, you go somewhere else and then again come back. So, in a function call also you do something like that, you go to a function, do it and come back, but there is one difference. For a function call, you actually make a function call from somewhere in the program. You know that in a program from this place I am making a function call, but here you do not know when the interrupt request will come. It can come here, it can come here, it can come here, anywhere. So, while your program is executing, your interrupt request can come potentially anywhere. So, wherever it comes, you will have to stop, you will have to go there, finish it and then again come back. Okay? Fine. So, just as I said, for a function, it is called from well defined places in the calling program, which is actually coded, and only the relevant registers need to be saved. Whatever registers you are using, you need to save only those registers and return, because the function might be destroying some of the registers your main program or the calling program was using. So, you should make sure that those registers are not destroyed. Okay? But in contrast, the ISS, interrupt service subroutine or interrupt service routine ISR, both are called ISS or ISR, they can get invoked from anywhere in the program which was executing. This anywhere means it depends on exactly where the interrupt signal arrived. So, potentially all the registers that are used in the service routine, service subroutine or routine, whatever you call, needs to be saved and restored. So, what I mean to say is that because you do not know where in the program your interrupt might come, and in the program you may be requiring a large number of registers in different parts. So, potentially you may have to save and restore all those registers. So, the overhead of saving and restoring registers and interrupt can be much higher. This we will see in detail later. So, pictorially it looks like this. This is a processor. The interrupt request comes from some device or some external source. Processor generates an interrupt acknowledge, and why this is required we shall be discussing this later. Okay? Because so far we have not talked about interrupt acknowledge, we shall see it later. Now, there are some challenges of course in interrupts, and these we shall be dealing with in some detail in our subsequent lectures. First thing is that for multiple sources of interrupts, if there are multiple devices interrupting, so how to know who has interrupted, and how to know what will be the address of the interrupt service routine, where to go, right? Because the service routine for the disk may be different from the service routine of the keyboard, which may be different from the service routine for the mouse. Okay. So, I have to know that which device is interrupted and where to go and how to know this. Okay. Secondly, how to handle multiple interrupts. What I am trying to say is that while an interrupt request is being processed, like the ISR is being executed, let us say another interrupt request has come. So, what do? Would you stop the ISR? So, there are many alternatives here we shall be discussing. This may require this enabling, disabling or masking of the interrupt systems. Nextly, there can be simultaneously arriving interrupts. So, how to handle? So, here you have to do something regarding prioritization of the interrupts. You have to define interrupt priorities. And lastly, there can be interrupts which can come from some other device, not only IO devices like exceptions, traps, other kind of devices. We shall be discussing these also in some detail. So, with this we come to the end of this lecture. So, in our next lecture we shall be continuing with our discussion on interrupt handling and interrupt processing. We will look into the different details, exactly what are the issues and what are the possible solutions we can use there. Thank you.